All right. Very good. Thank you all for coming this morning. I appreciate you taking the time. Um, First, I'd like to talk a little bit in terms of an introduction of myself. Mike Shido, I'm president of Americas for George Utz. I've been in product development, manufacturing, logistics for 30 plus years now, 12 years with Utz, developing the company locally in North America. The Utz Group, just as a quick introduction, we produce in 8 different locations throughout the world. So we produce in North America, that's in central the United States, as well as in Mexico, Asia, and Europe in 8 different locations. Also, as an introduction, not only do we have a global sense of markets and global footprint, we also have the view of solutions across many different markets. So I would say the 2 things that we allow us to offer is both that global look and then also a cross-market look where we can take solutions that might be developed from one part of the world or from one market to the next market and share them with our customers as we develop new products. So that was only just to give you a general foundation of the background of the presentation. So what are we going to talk about today? Today we're going to explore how do we improve return on investment for returnable packaging. And I'm talking about that in a more holistic approach. I'm not talking about an individual given project that is one specific component conversion from a expendable to a returnable, but I'm talking about it in a total view of your business. Well, we talk about return on investment. The other important aspects of that is the speed to market, our ability to scale. These are all also important aspects and outputs associated with this kind of approach. So before I get into some details of some specific projects and approaches, I wanted to at least touch on returnable packaging. So returnable packaging in general has some certain elements that need to be considered when we think about when does it make sense to do returnable packaging. The first, of course, is being a closed loop situation. So when we think about when to adopt returnable packaging, you need a controlled closed loop environment so that we can control these assets. The second point is that you need a certain level of volume. It doesn't necessarily have to be high volume, but you do need volume and these repeat turns associated with returnable packaging. Other attributes might be interesting is high value goods. Valuable goods allow you to invest more in your packaging. Sensitive products along the same way. When you have common families of products or common approaches across your manufacturing location, you can also look to adapt different methodologies of returnable packaging within your loops. And when I talk about loops, these are both internal and external loops. And I will explain some of these loops in just a second. So why returnable packaging? First point is obviously the general payback. That's the one that everyone always thinks of, the economical aspects of replacing the expendable products in terms of cardboard or whatever that might be with a rigid returnable. Very simply, you buy a $10 plastic box, you can cycle it 100 times, and a cardboard box costs $2, and you get a payback within 5. You got 95 returns where you're getting payback. So that piece is very straightforward and clear. But then we have also the clear challenges of waste reduction, improvement in quality when we talk about protecting sensitive parts and rigid containers versus expendable versions, improvements in safety, enabling standardization, and the vehicle for standardization and driving standardization through your operation. Now, this is a real key point, that the returnable packaging, the standardized returnable rigid device can be the platform for you to standardize operations throughout your facilities and even in your value chain. So let's talk a little bit about different families of returnable containers. There's groups of returnable containers. There's what I would characterize as industry standards. These are things like automotive straight wall containers, AIG approved, or bread trays, or pallets, these kinds of solutions which are standard amongst the industry. And then the group you see on the left-hand side are more what we would call customer-specific, product-specific solutions. These are solutions that as a manufacturer of goods, you can take advantage of within your own universe, within your own supply chain, to standardize and optimize your operations. So here's a view of the typical loops we see in the supply chain. We have in the middle the device manufacturer. Then you see certain loops that are feeding into that manufacturer. You have loops that come from external suppliers. There may be a loop that's associated with the internal suppliers. There's also even loops potentially coming from overseas or international suppliers. Then on the output side, there might be a buffer loop depending on your industry, and then eventually into a repack or an outgoing shipment to an OEM or an end customer. Though that particular area, the end piece, so this is kind of showing you the two different families where they're used. The end piece where you're shipping to an OEM or the end consumer, those tend to be standard industry solutions. I'm going to focus on what is the customer-specific solution. So as I'm making goods, how do I optimize my operations? So the presentation is focusing very much around the customer standards. So what is the vision here? What we're trying to do is we're trying to not just transport goods. We want to add value to the process by tying manufacturing processes together via a common returnable solution. And so that is the main thing. We're not just transporting goods, we want to add value to the process. So what are we considering in these strategies? This really comes down to our ability to be fast in the marketplace, our ability to scale, ability to be flexible, reduction in administrative costs, the sustainability piece, and so forth. And of course, reduce our packaging costs. So how do we do it? We had the first principle, we want to tie manufacturing processes together. So the output of process A is going into a returnable transport device, and it is the input to process B. And it's important that those things, and especially if you're driving towards automation, that you understand that that standard piece needs to be handled in both operations. And those operations may be in your facility, or they may be actually at a tier 2 to the tier 1 scenario. But using that standard input tray or returnable packaging will allow you to optimize those automations, specifically if you're talking about going to automation. And where do we think about standardization? It's can be done in families of parts. It can be done regionally. It can be even done internationally. So we have customers with the same standard approach that is used across the globe in terms of how they handle their parts and how they interface with their machinery. So what do I mean when I talk about standardization? Here's an example. You can see in this case there's 8 individual trays with 8 unique components in this example here on the right hand side. But what you'll notice is that the transport tray that they're in is very much unique. It has a common footprint, it has a common outside geometry, it has a common way of how it's indexed, how it's located in automation, how it's conveyed. And each one of those products actually is off the same tool with different inserts. But you can see when I say standardization, that's a standardized approach across families of parts within a given facility. The last tick there is the business processes, and this where it comes into the next slide. When we talk about if you do standardize and you start to standardize, like in this prior slide where you had all of those components in the same framework of tray, you can now essentially start to standardize your business processes. So what happens in a one-off development of a returnable packaging solution? You have these typical steps in the project development. You go from concept to sourcing to final design, tooling, and so forth. And I want to compare the difference between a standardized approach and a one-off approach. So if you look at a one-off approach in the circle above, as you're talking about developing the products, there's a bunch of work that happens on the front side, right? So the customer or yourselves are developing a set of specifications, an RFQ on the project. You're sending it out to the vendor base. Multiple vendors are quoting with different solutions. They're submitting quotes. Then you go into a sourcing phase, and there's another loop of that where you might look at the requirements again, another set of development, some questions back and forth. There'll be analyzing of quotes. If you take that with a standard approach and look back to that first slide, that slide I just showed you, which is if you had that standard approach, which was the standard tray, that process from concept to sourcing is almost no work at all. It's already given. The work is we're taking part A and we're putting it in tray B, and we're going to work out the geometry. What work needs to be done? Everybody knows what it costs because you buy it across all of your product. Everybody knows what it costs to tool a new derivative. Everybody knows what the timing is. The guys who are building the lines know exactly what the geometry of the product is, so they can very quickly adapt. And in this case, there's almost no work from an engineering, development, administrative side, purchasing side as well. That's just showing it again on the final end of the design. If you can imagine in the development process, now you get to the final design, you have to approve drawings, go through the whole validation process, and so forth. In a standard scenario, the frame itself already exists. You already know how it's going to index, how it's going to locate. It's even coming off the same tool. So there is very limited work in this end of the process. So in general, in summary, if you look at the difference between doing it one by one, each program one by one, individually, and taking packaging, I would say, to the tail end of the development process instead of standardizing and doing it up front, you end up with, on top, a very complex, multi-step process of product development that has many handoffs and many potential failure modes, as opposed to a very simple, standard, straightforward approach, which allows you to go very quickly from initiation of the program to realization. This slide actually just shows it. I mean, the main point here is that you're actually reducing all of the administrative piece, and the value is actually in the reduction of the administration within your organization, the time wasted, the redo wasted, and of course, there's a reduction in the packaging when you standardize and you get economy of scales, but that's not the real carrot here. The real carrot is to be able to do it over and over again, scale, and do it highly efficiently, and especially if you're in a hyper growth, where you have a successful product and you need to add a new line, or you need a next derivative, or you need to move to an international location. The only way to be able to do that is with these kinds of approaches, to do it and do it efficiently. I'm going to touch on a few examples here of different solutions that have been done and standardization that we've done with our customers. We focus on two primary processes, and I'm going to highlight these two processes because there's certainly some differences between the two processes and some advantages and disadvantages of each. Thermoforming and injection molding. Just an overall description. Thermoforming on your left-hand side, which starts as a flat piece of plastic, essentially a plate. It's formed over a mold. This process is interesting because it's very low investment. You can still include it and use it in automation. It's got short lead times, and you can turn it around. You can also use it in this I would say, this standardization approach that I talked about on the earlier slides. That was actually a thermoform. On the other side, high pressure injection molding, which tends to be a process that's aimed at high volume manufacturing. It is a little higher in investment side, typically lower in piece price, much longer lead time, less flexibility to change. This slide actually represents kind of a break-even point. It compares those two technologies together, and the reason I highlight this is oftentimes we'll have customers who believe that they may not have the volume or to create a business case associated with a returnable solution for a given loop. And if you look at this chart here, the lower is a thermoform. It starts out with a low investment but slightly higher piece cost, and injection molding, which of course starts with a higher investment and a lower piece cost. You can see that crossover is somewhere just north of 10,000. So once you get above 10,000, injection molding certainly seems to make sense. But it doesn't mean that if you are below 10,000 that you can't have a solution associated with a specific, component-specific returnable solution. We can do that in thermoforming. The other is the development time. This is only just a visual to help you demonstrate the overall difference. If you have a rather short lead time, low volume program, thermoforming and thermoforming trays is clearly the answer. And then this slide actually shows you in a more visual way, again, going back to the slide with 8 different components off of the same tool. This is actually how it happens. So you can see the tool is there in the middle, the silver part, and then up top is a little schematic of the tool. When we talk about going from one component to the next, the only part of the tool that's changing is the red block that you see on the top of that colored schematic. So instead of buying for each program a $7,000, $5,000 tool, you're buying a $1,200 to $2,000 insert for each alternative change that you do in terms of new component that you put into this given tray. And it's not just the cost, it's the sheer fact that you don't have to develop it, you don't have to test it. It's simply when we have these kinds of, I would say, standardization programs with our customers, literally it's put it in tray B, send us the CAD data, and we develop the plate. And actually, the component actual cavity is developed in SLA. We do a rapid prototype of it, and that's where the prove-out's done before we tool. So it's a very efficient, very low-cost approach. I use this one as an example of, and because there's so much ASRS activity that you see here at this particular show, but this is a family of containers, again, a standard associated with ASRS. You can see that it is like containers, but with quite different functions and features, from ventilation that you might be using in a refrigerated environment to removable containers for small parts or aftermarket parts supply, interchangeable dividers, even different bottom configurations. But again, all off the same frame. So it's the same footprint that an integrator might use, and he can adapt those different solutions depending on the products, from textiles that might need a light bottom with a full open container to small parts manufacturing, or screw machines or heavy machine parts that need a much heavy double bottom welded configuration to support 120 pounds in the system. This is just an excerpt from a white paper which we're publishing shortly that we did with Polaris, and it actually talks to just a quote out of that about the flexibility associated with this solution, and the ability that Polaris was able to take this one family of containers and be able to use it from big parts into small parts, and to organize those small parts in a way that they could easily handle them in their distribution center. So the last case study I want to share with you is a video controller. So this is a controller development. They wanted to put together a complete video controller, all of its component parts coming in various ways, bringing them into an automated work cell, and then putting them together with no one touching it at all. So we had, again, very similar in terms of the loops. There were external suppliers, there were internal suppliers, there was actually overseas suppliers, and then there was also even the need to pack, again, the product once it was in the finished goods stage before it was packaged. So what did we do? We actually developed 2 different footprints. One footprint taking 14 of the components and putting it in the same tray. So if you can imagine the inputs into this cell, all of the cell inputs were exactly the same. Tray inputs, stackers, destackers, pallets, and so forth, but not just at the assembly station. We were able to drive those trays and bring them back to the tier level. So as they were coming out of the manufacturing process at the tier level, they were automatically going into trays, being stepped out on a pallet, and being able to be automatically moved into the final assembly. So this is the second tray, which we put 5 components into. And then we even came up with a solution for the overseas scenario, where they have the overseas parts were coming in small, very flimsy thermoform trays, impossible to be able to put into automation. But we took the idea of a rigid tray that we could snap the incoming trays that we were getting from overseas into this transport tray and then index it into automation. So even the overseas parts we were able to put into one of the tray variations as well. So what did we end up? We ended up with 19 different unique trays, really only on 2 footprints. The customer's original intent was low volume injection molding and even some machine carrying and pick and repick operations. We saved them $1.2 million just on the investment. But think about this as well. The next the next set of controllers, or the next change in controllers, how quickly they're able to adapt associated with the process that they had, or if they need to scale this. They already have this, all they need to do is duplicate it. And it's not duplicating in its totality, it's duplicating each one of these modules. So now I'm going to share with you a video. This is a video that actually was done by the machine builder that actually shows this particular study that I just talked about with these 19 individual trays. But it's a kind of a time lapse of the system being built up. Interesting stuff. So you could see all of those trays coming in from the peripheral, but if you can imagine all of those processes tied together, tier processes into the manufacturing process, all being facilitated by a common transport tray with unique inside dunnage that corresponds to the automation. I think you need to release me for one more slide here. So, yeah, in summary, just a few key points. One is think strategically. Think strategically across your business. Don't think individual projects. Execute your packaging strategy, your manufacturing strategy across multiple programs, across your business. Try to group them together. Try to figure out how to standardize to allow you to take advantage of all of the things I talked about, reducing cost, scalability, speed. Start with the business case. That's always important. Understand your ability to invest. Do that early. Engage your whoever your vendor or set of vendors might be in terms of who's going to develop the returnable transport device early in the system, not late. Again, move packaging or the transport of goods earlier in the development process. Don't wait till the end. And then use discipline in the process, and then drive standardization. And the last point, don't just transport goods and tie manufacturing process together to get value.